Thank you, everybody, and thank you to the committee for organizing this great conference. And it really has been lovely. And it's really been lovely to meet with so many people and the collaboration and to come together after this time of remote work. Today, I'll be talking to you a little bit about anomaly detection in real-time alert streams, but mostly I'll be focusing on the photometric classification and first data release of the Young Supernova Experiment, which we just heard a brilliant talk from David Jones about. And without further ado, we will get right into it. So I'll briefly cover kind of two active time domain surveys, ZTF and YSE. And in that work, I will talk about some of the brokers of LSST, specifically the Antares broker, and my work developing an anomaly detection filter with Kostya Melanchev, who also spoke earlier today. And from there, we'll transition into some of the preliminary results from our first data release from the Young Supernova Experiment, and just talk about some interesting trends that we found, or classification studies, and kind of what our data set looks like, and when you can expect to use it for your own science. So this field of time domain surveys has a pretty broad span of different types of objects that people are interested in, like pulsating objects, stochastic objects, or transient objects in their nature. For this talk, we'll really only focus on transient type events like supernova, thermonuclear type 1a, and core collapse type 2, and type 1bc. And but there's a whole breadth of time domain objects that people are interested in, but today's talk will just be on kind of the transient nature of these objects. And one of the great facilities for researching these transient like objects is this Wiki Transient Facility, which we heard a little bit about earlier this morning. It's a Northern Sky survey that observes with a cadence about every 2 nights, and primarily 2 filters, and has been hard at work the past few years discovering many transients and doing really good supernova science, variable star science, microlensing, all these types of science. And if we look at kind of the breadth of a lot of these time domain surveys, we see here a plot of the different field of view of these, like ZTF, upcoming LSST, and Pan-STARRS1. And on a typical night, we get a few 100,000 alerts within the nightly ZTF alert stream. And alerts being just any object that changes in brightness or position in time. And soon, when LSST comes about, that is going to elevate to about 10 million per night. So the field has had to develop some kind of system to ingest all of these alerts and process the data and make them in a usable format for scientists like us to use them and to do our meaningful science with them. And so in this, scientists have developed these time domain brokers, which I like to think of kind of like a bank. Maybe it's not the best analogy, but this is kind of how I think about it, where there's money that you have or would like access to, so you need to go to a bank to kind of withdraw it, and these brokers, like the bank, act as an intermediary between the money, or in this case, the photometry and like Coast Galaxy and this alert data, and then you. So I like to think of it, I go to the broker, get my light curve data, and do some interesting science with it. And in that, there's a whole scale of all these different like bona fide LSST brokers: Bobomol, Ample, LRSA, Lasser, Fink, Pitt, Google, and Antares. And I think there's representatives from most, if not every, broker team at this conference, so it'd be a good chance for us to talk and coordinate. But in a main sense, they're all trying to work towards the same goal, which is to process all of the nightly alerts from ZTF and then scale up to LSST. And from there, effectively distribute these alerts in a way that people can use them for their meaningful science. One of the nice things that I used with the Antares broker is that we can custom make a filter, which is just a piece of Python code to do kind of whatever we want. And I decided that, hey, I would like to look for some real-time weirdo objects in the night sky and the nightly alert stream, and then coordinate some follow-up. And so one of my past research projects was working on a real-time anomaly detection filter, which was a simple isolation phase isolation force-based algorithm trained on 1 million random and tar-race alerts, and using light curve, extracted light curve features from their data. And I would just like to highlight 3. One was 2021 QDL, which is a microlensing event. And in the middle there is 2021 TDU, which is a luminous red nova discovered in the Andromeda galaxy and is the only fourth observed luminous red nova in Andromeda. And is the least bright of all of them known to date. And then this guy on the right is a pretty new one, which is a calcium-rich supernova. And as you can see, we discovered these kind of events early on in their observations before peak, where we've had time to coordinate with our spectroscopic follow-up resource partners to get observations and classifications of this data so that we can continue our intensive study of these objects. And as you'll hear, I think, at a later talk from Ashley Villar, and that we also heard an early talk from Kostya Malachev, is that we really need to find these like needle in the haystacks and act on them quickly, because in the nature of these transients, some don't last very long. And with LSST, which will only return to the same patch of sky in the same filter every 10 nights, we really need to utilize these other surveys like ZTF, like YSE, and other spectroscopic resources to follow up these objects in as real time as possible and investigate them while the interesting physics is happening. And so once we discover these anomalies, we report them to TNS and then use some kind of follow-up resource or recommendation system. And I should really have refit on here. That would be a great one from this talk that we heard earlier. That would be wonderful to add. But I just want to highlight the one on the right, which is the Young Supernova Experiment, which you just heard from, which is based off of the Pan-STARRS telescopes. It has a similar cadence and exposure time to ZTF, but if you notice, it has, in its filter set, it observes in redder filters these INZ filters that enables you to probe into these redder regimes and intrinsically fainter objects. And it's kind of got the most analogous filter set for what we will see with LSST, as Dave just said. And so a lot of the data and the work that can come from this will really help prepare us scale up for LSST in actually a few short years. And there are many people within YSE with many diverse science interests, some of which are listed here. Young supernovas, you can expect from the name, but also just rare and fast transients, which is what I'm interested in. But then there's a whole host of cosmologists who want to use type 1a supernovae for their cosmology and wanting to get a sense of black hole variability and TDs and rare things. And so if you kind of fall into one of these groups, maybe think about asking to collaborate on one of our projects. So the Young Supernova Experiment first data release, what does it really comprise of? So it spans the first 2 years of the survey, just thereabouts, with a tad under 2,000 supernova-like objects, of which about 22% are spectroscopically classified. And we have everything from host galaxy information, photometric redshifts, host galaxy redshifts, if they're there, spectroscopic classification, photometric classification, and those percentages, as well as many other types of metadata and the light curve data. And if we take a look into our spectroscopically confirmed sample, we can see kind of the breakdown of these types of objects and their unique classified type or subtype. And YSE has a few criteria for its spectroscopic follow-up, but two kind of main sub-surveys, you can think of them. There's a magnitude-limited sample and a volume-limited sample, where the magnitude-limited sample is trying to spectroscopically classify everything brighter than 18.5 magnitudes, similar, the exact same criterion as in the ZTF bright transient survey. And then there's a volume-limited survey, which is trying to spectroscopically classify everything within 250 megaparsecs. If we compare that to the literature, and again, I should preface, this is still preliminary, and a future real in-depth census relative rate result paper will be written. But if we compare it to the magnitude and volume limited samples out in the literature, we can see that although the agreement is marginal, we still do agree with the literature results of the ZTF Bright Transient Survey and Assassin Magnitude Limited surveys. as well as the ZTF census of the local universe for the volume limited survey. Some very kind of real prominent objects that YSE has observed in its few short years as an active survey is 2020 OI, which was a paper led by Alex Galliano, who is here in the audience. And this was a type 1c, which is the dimmest 1c event with known flux excess unassociated, likely to be associated with some shock cooling. And then I also worked with an undergrad, Philip, who was able to take the information from our data release and from Alex's paper and use Maria Vincenzi's PyCoco code to build an SED model to then integrate into simulation softwares like SNANA to make simulations for future surveys to keep improving the simulations to help shorten the gap between simulations and real data. Some other highlights you will hear in talks coming up soon is Sam Ward. He'll talk on Friday about this 3 type 1A system, specifically on 2021 HPR and all the cosmology that has been done with that, as well as 2020 NOV, which is a TDE that has excellent easy photometry that you'll hear a talk from Nicholas Earl about, I think tomorrow or very soon. So the general pipeline of YSE is fairly simple. There's some transient that goes off in the night sky, and YSE observes it with our telescopes, and oftentimes, because YSE likes to coordinate its observing schedule with ZTF, there's a lot of shared fields that they observe at the same time, and so oftentimes there is interleaving ZTF photometry for our objects. I think over 90% of our sample in YSE Data Release 1 has complementary ZTF observations, which we do leverage in our photometric classification. And sometimes if the object is bright enough or interesting enough and we have the spectroscopic resources for it, we go and get a spectra, or maybe somebody in the field has also found it interesting and gets a spectra kind of for us, and we do borrow those classification labels. And one of the things that's important about developing a photometric classifier is that you need some kind of measurement on the redshift to use in your classification. And so the first piece of that starts with kind of the host galaxy information and what kind of data and things you can learn from those associations. And so we use 2 codes, Ghost, also written by Alex Galliano, and this other code called Sherlock, written by David Young, which are 2 host association codes that we use to first algorithmically associate all of our supernova-like transients, and then we went through and vetted each association to make sure that the associations were correct, because sometimes algorithms get stuck in a H2 region, or there's some artifact in the host galaxy stamp that they use. And so with these host galaxy associations, we can query for host galaxy redshifts, which we can use in place of a redshift. And then if we don't have any of that information at all, we have to look towards photometric redshifts. And it's been predicted that with LSST, only about 0.1% of all LSST transients will have any type of spectroscopic supernova redshift, and from there only a small percentage will have a host galaxy redshift, and so the overwhelmingly vast majority will need to use photometric redshifts. And so we use this code from Andrew Engel called Easy Photo Z that we use to calculate a photo Z that we use in our classification, and we can see that the scatter is pretty well contained, and that if you compare the spectroscopic redshifts to the photometric redshifts, we do get a pretty close agreement there. So now I'm going to transition my talk into simulations, which is what we actually use to train our photometric classifier. And so we use this code called SNANA, developed by Richard Kessler, to make our simulations for us based on the Young Supernova Experiment and the ZTF kind of cadence and sky brightness and the kind of survey information. So we were recreating simulations that we would see as if we were using ZTF and YSE resources. And so we simulated about 60,000 type 1A, type 2, and type 1BC supernovae for our classification. And these are the three classes that will be used in our classifier. We don't classify superluminous supernova or even the subtypes of type 2. We don't discriminate between type 2 and type 2N. It's just very broad, type 1A, type 2, and type 1BC. And I've worked quite extensively with an undergraduate, Sami Sharif, who used a parametric fitter equation from Ashley Villar to fit both the spectroscopic type 1As in our sample as well as simulated 1As, and used a KD tree method to find the closest match between simulations and real data so that we could start to convince ourselves that the simulations were characteristic of our data set and the YSE first data release, so that our classifications would be strong as a result. And even if you just kind of squint your eyes or just look briefly at it, you can, it's hard to tell between what's simulation and what is real data. And so as Dave did mention at the end of his talk, I adapted Kyle Boone's ParSNIP architecture, which is not the root vegetable, but is a variational autoencoder that we use simulations to train with. And the goal of ParSNIP is to disentangle kind of the observing properties of observing a transient with its intrinsic physics. And it tries to do that with its representation of explicit latent variables and intrinsic latent variables in that space, where the intrinsic latent variables try to characterize something intrinsic to the physics of these transients. And we use these features from this intrinsic latent space into a random forest classifier, which we use for the actual classification itself. So we train exclusively on simulations and then test on our spectroscopic sample. And that looks like this. So if we just use our three types of type 1A, type 2, and type 1BC, this is how ParSNIP does on our 437 supernova that fall into these classes. And so if you think to the completeness and purity metrics, completeness is just out of all true samples of a type, how many did you guess correctly, where purity is out of how many of a type that you guessed, how many are those of actually that type. And so if we look at the completeness and purity confusion matrices for our results, we can see that for type 1A, we have very strong completeness and purity, which will be great for our cosmology-related type 1A studies that will use our photometric and spectroscopic type 1As to do our cosmology. But there is kind of confusion between these two core collapse supernova types, which isn't unexpected, as these light curve profiles are fairly similar. But we do notice we do have a very high purity of type 2 alone when we look at that. And so when I was looking through kind of the data, I was saying, the intrinsic latent space is only described by 3 parameters. Let's try and plot them to try and get a sense of this, kind of black box latent space. Like, what does it really mean? What is the algorithm thinking? And how can we kind of understand what it's doing so that we can better understand our data? And so here is a GIF of a 3D scatter plot of our intrinsic latent space from our ParSNIP classifier. The colors represent the different supernova types. The little faded dots are the simulations that were used to train the variational autoencoder that are mapped onto this space. And then the classification is represented as a triangle, where the true classification type is a right side up triangle, and the predicted classification is the upside down triangle. And you can see that they naturally group in these kind of 3 distinct clusters. The type 1BC is way more spread out than the core collapse type 2 and the thermonuclear type 1A. But you can see that the algorithm likes to separate them, or likes to group them into these some kind of meaningful intrinsic space. And most of the classifications, the misclassifications we find, come from objects that are way outside kind of their core distribution, which kind of makes sense. It's maybe it's a type 2 that is unusually, bright or unusually short in its duration or something, and somehow ParSNIP is still encoding that information into this latent space. And so a real more thorough investigation still needs to be done, but this is just kind of an interesting step into that regime. So if we collapse our core collapse classes into two, into this broad class, we can see that we do very well on our photometric classifications using these photometric redshifts, again, trained on simulations of our real data. And again, this gives us confidence that we'll be able to classify and characterize our photometric sample correctly, or as correct as can be for now, which will be important, especially when LSST and these really large scale time domain surveys come about, and we need reliable photometric classifiers that are quick and can update with new observations and new contextual information. So once we have our classifier, we can characterize the remaining photometric sample that have yet to be looked at, and we can see kind of how this breaks down in comparison to other surveys like the ZT upright transient survey and the Assassin survey, as well as comparing against another really excellent photometric classifier called Supernovae. And we can see that these percentages of type 1A, type 2, when we see more or less kind of fall into our expected percentage ranges of what we would expect from our observed rates. So just to conclude, soon, hopefully in the next few months, ideally a few weeks, we would like to wrap up and soon put on archive the first data release of the Young Supernova Experiment, which again encapsulates the first 2 years of the survey. It can be used for cosmology studies, or just prepare for Rubin, or to test your own photometric classifiers, or to look for anomalies, or any type such thing. And the release of this work not only has the data release, but also has all the information about our photometric classifier, how we trained it, what are those results. So it's very much a data photometric classification focused data release paper, and it performs well. DLDR performs well, and we're happy with it, but you want to keep working on it and keep extracting and leveraging all the information that we can get from images and light curves and metadata and everything we can, so that we can develop these classifiers and give us our best chance of classifying the time domain sky. So with that, thank you very much, and I'll take questions.
Great. Questions in the audience? You have one?
Sorry, you had some thoughts about the misclassifications for the confusion metrics, right? So how does your training sample biases correlate to this? So I know you mentioned about extreme situations where it's like a super bright supernovae or super faint, but can you comment about the biases that your training sample has? So.
Sure, absolutely. So it's a really wonderful question. Our training set is based off of real data itself, so we do have the same kind of redshift ranges and the same types of filters. We looked very much into even the total number of observations per filter that we observed in the real data and in the simulations, to make sure that those comparisons were pretty equal. Though it seems that the biases mostly come from deficiencies in the simulation, where there are, even if we look in the latent space, it's hard to see, but there are gaps where there's observations of real data where there's no simulated reference mapped into that same space. And so I think a lot of these classifiers aren't very strong at extrapolating kind of these weird oddball objects, and a lot of the misclassifications come from very rare subtypes like these broadline type 1Cs, which don't have many spectroscopic spectrophotometric templates. And I think, yeah, and so I think the biases in our training sample is honestly more related to the fact of a underrepresented simulations in the types, the diversity, as opposed to like a different redshift range, or like not the right cadence or filter set or something like that. So yeah, it was, thank you, yeah. And I just wanted to add, and that's why we were working with Phillips and soon new undergrad students to take some of these rare supernova-like things, like a superchangeless SACAR type 1A, and make SED templates of that, so that we can use them in future simulations, so that we can keep iteratively improving classifications. But yeah, thank you so much.
Thank you. Any more questions? I have one,
Yeah, please.
if I may. So you're showing a few confusion matrices for the 3Ks and the 2Ks. So I assume that you're using some threshold on probabilities, right?
Threshold for?
For probabilities. You're deciding the classes, right? So do you calibrate the probabilities, or you set a standard threshold?
No, we're just kind of using the standard output probabilities from the classifier, and just choose the one that gives the highest classification score.
And so on those thresholds, are you setting up across the board the same threshold for all the classes, or are you tuning up the curves for each one?
Yeah, so we're not doing any specific threshold per class. It's just whatever the classifier will output a percentage confidence per each class, and then whatever is the maximum, we take that and use that as our classified score. And I don't have a plot here in this talk, but I have a distribution of its confidence scores, and there could be some future work done in trying to scale those confidence scores appropriately. That could then inform some of our classifications, but for now we don't do anything smart. It's just whatever's the maximum probability, that's the classification we assign.
Okay, great, thank you.
Real quick, I didn't catch if you attempted to address the class imbalance, which is obviously at root of, in part, why it's the 1BC problem remains. Did you, like, you used real data, then you created simulated data, right? Did you try to augment to address the class imbalance? Depends on your classifier. Sometimes it's advantageous to not try to augment and then worry, but I just wondered what you thought about.
Sure, we do rebalance the classes to more or less model the ZT bright transient survey rates, and
but how?
But we use
yeah. Sorry, you're going to answer it. But how?
So yeah, so this is done not during the training, but it is done in terms of the feature set that we use into our random forest classifier, which then informs the classification results itself. So it's kind of more downstream from the architecture. And we did test if we don't inform the rates at all, or don't do any kind of changing of this balance, and we do get a kind of similar percentages, but in fact it does lower, if I remember correctly. It under guesses type 1As, the number that we would expect just from our local observations, especially from our magnitude and volume limited surveys, which I showed earlier, and those percentage breakdowns.
Yeah, I asked, this is a sticking point for us. It's a nagging problem about how to properly address this. Thankfully, when LST turns on, we should have many more events, but we'd like to be able to prepare for it. And then a big comment, people need to get used to probability transient types, which is to say we can't just think of things as 1As or 1BCs anymore. These are going to have fractional classifications associated with them as we push deeper.
Yeah, and we have to get used to updating classifications too with new data. So, absolutely. Thank you.
Thank you. I think the last one, if this chart?
It's really cool that you're able to use both ZTF data and YSE data in your classification. I was wondering if you have a sense for like how much adding ZTF improves your classification versus just using your YSE data.
Right. ZTF helps quite a lot, actually. One, because of downtime with YSE or something, and YSE has a filter selection that emphasizes the GNR bands, but we do like to observe in I and Z. And so sometimes there will be epochs where YSE is observing in these kind of redder bands, and we don't have this kind of more green, bluer bands to observe in, and then ZTF fills that in. And we did a lot of work to make sure that we could contiguously use kind of both ZTF and YSE. And if you count just the number of observations of the first data release, I don't remember the exact percentage, but ZTF contributes quite a lot in terms of the number of observations that we use. And so the more good data that we have, the better it is for our classifiers. And so it does help a lot. But yeah, wonderful question.
Thank you.
Thank you so much.
Yeah. Thanks to the speaker.
We hop back to